name is John Kowalski. I'm part of the marketing team here at Vic Gardner. And today we're talking dispersion, actually going a little bit deeper than usual into dispersion, doing a deep dive here. So this is part one of our pre-dispersion process. We'll do a milling deep dive down the road just a little bit. We are recording this, and immediately following the presentation, you'll receive an automated email with a link to that recording. Please feel free to share that with colleagues, look at it at a later date or whatever you'd like. Also, if you have any questions, please log them in the chat box located in the bottom right-hand corner of your screen. And time permitting, we'll get to them. If we do run out of time, we'll record those and reach out to you individually. So with that, let me introduce our resident dispersion expert, Mr. Andy Stummer. I'm sorry about that, Andy. Andy Stummer. He is our business line manager for our dispersions. So with that, Andy, it's all yours, sir. And Andy's calling me. Okay.
But I think we're good to go. So thank you everybody for joining us today. So as John alluded to, this is the dispersion deep dive, the first part. We're going to cover the pre-dispersion process in a more detailed fashion. And the second part would be more about the milling part. We covered that a little bit, but this is mainly about the pre-dispersion process, and we'll cover also some different technologies. Okay. All right, so we're going to have a quick introduction about VMA. Then we dive right into the actual dispersion process. We're going to talk a little bit about the different lab and production equipment solutions that we offer, and then a little bit about the QC process, and then some of the lab capabilities that we offer here in the US in Wallingford or in Germany at VMA headquarters. We have an outstanding applications lab where we can do a lot of trials and also upscale trials for production equipment. So VMA Getzmann is a German company, was founded in 1972 by Hermann and Elke Getzmann. That couple on the top right. Vic Gardner has had the exclusive distribution rights for the product line in North America since 1988. Vic actually has used that equipment for quite a bit longer throughout the laboratory space in Europe and the US. And what happened was some customers came in and saw the equipment run at the Big USA facility, and they wanted to know if they could purchase that equipment. And that was the starting point back then when I think it was Dr. Peter. He decided that we would include that in the product line of our big instruments group, and that's how that whole thing got started. So the company is still family owned. They have over 100 employees worldwide. They're known to make really high quality dissolvers, bead mills, basket mills for lab and manufacturing environments. They also have the Dispermat trademark that you probably have heard before, so they own that name as well. So here is just a quick slide about the company. So you have that building in the middle. That L-shaped building is actually new. They added more split space for design, more office space, as well as more manufacturing space. The company is really flexible to different customer needs. So about 40% of all the equipment that VMA manufactures is custom. So we have a lot of applications where customers require certain components like a nitrogen valve, or we want to flush inert gas through chambers, or want to build a reactor, or those kind of products. We can actually help there and develop a solution with the customer. And VMA is really an expert at that. And then They have a really nice lab. I mentioned that earlier in Germany at their headquarters. The company is about 30 miles east of Cologne. So if you're ever over there and you want to visit the facility, let us know and we can set that up. And the lab in the US is at our sister company's facility at Big USA, and that is up in Wallingford, Connecticut. So, just a quick introduction. How do you use Dispermats and where? And basically, we were born out of the coatings world, and they were first and foremost really used to disperse pigments. Over the years, the instruments have found new end use markets that we are in. Obviously, battery is a big one, oil and petrol, pharmaceutical is another one, agriculture. So there is a lot of different end use markets where they would be using that type of equipment. But when we talk about dispersing, we really differentiate between different pigment classes. So we have these organic pigments, we have inorganic pigments, we also have functional pigments and the special effect pigments. Uh, some of you know those well. These are these silver flake effect colors, which have to get dispersed with a little bit more care because you don't want to destroy those special effect pigments that would ruin the effect. So that's done a little bit differently. And the whole purpose of the dispersion process is to really improve our overall appearance. We want to have better gloss, transparency, color strength, and some of these major attributes that we are actually impacting by having a proper dispersion. So this is a great slide. It really outlines it well. So we are looking for improvement in our wetting process. These van der Waals forces, some of you who have a physics background may have heard about that. These are these invisible electromagnetic forces, binding forces that hold these pigment particles together. And then we want to actually reduce those clusters down to the primary particle size. That will give us better color, better gloss, overall appearance is improved. We get better pigment efficiency that will help us reduce our raw material costs. We have more product consistency. Formulation improvement is another net result of having really good dispersion, and also we get a more consistent particle size distribution. And finally, we'll also get better upscale results, which is really important if I want to go into manufacturing and I want to use the data from my laboratory scale or my pilot scale process and then go into production. So that's why we're doing it and why that process is really important. So if we don't follow a proper pre-dispersion or dispersion process, it's going to lead us to just poor quality of our product. So we have issues with color. There might be a bigger delta between the different lots. Poor stability of our product, also flocculation of pigments. Obviously, Big USA is really good at helping in selecting the right type of additives that will go in to the formulation that would help avoid those kind of issues, especially with the flocculation, sagging, leveling, settling, some of these other issues that occur. And then gloss is reduced. Increase in haze is another one that's not on there that's coming up. And then obviously the separation is also another issue that happens if we improperly disperse. So it's really important to remember that we need to get good stability, to have better color fastness, and that helps us with fading over time. Also, our brightness will be improved. That will give us the best color. The rule of thumb in terms of pigment size is that the smaller our pigment particles, the better our overall appearance. And that will also allow us to use less pigment and cut down on the volume, and that should help us reduce cost and save money if we properly disperse our pigment because we don't have to use as much. And usually, the lower the viscosity, the better the particle size distribution, and also it helps us with processing the material. Obviously, there is a threshold. Ideally, we are looking between 3,000 to 10,000 centipoise. That's a really good range where we're able to process the materials really well. If we are lowering viscosity, it's not an issue. But what that usually means is we have to put in more energy because the material is so low in our viscosity that it's more difficult for energy to get introduced into the mill base. So we have to either drive with more watts, or we just run a different tip speed. So there's some options to compensate for that. We'll talk about that. And then obviously, if we are too thick, that gives us different issues in terms of processing. If it's like peanut butter, it's very difficult to, for example, have the blade properly move the product. That would then, in some instances, require a sweeper blade to really make sure that the product is properly, moved around the container, and then that the actual blade can take over and really disperse these larger particles. When you're milling, that's also a big issue. If you have a very high viscosity, makes it very difficult to process in some cases. For example, a basket mill is not, it wouldn't be possible to use that technology just because the product wouldn't flow into the basket and then come back out. So that's why we have to use the
Hold on, folks. It seems like we have a bad connection here with our speaker. Andy? Okay, looks like he's trying to work on some things on his end. Please note we are recording this, and hopefully we can get it going again here. And then, Andy, you may have to drop off and then relog back in perhaps. But we are recording this. You'll receive a link. If you have any questions, please log them in the chat box located in the bottom right-hand corner, and we'll get to them as soon as possible. Andy, if you can hear me, you may need to log out and then log back in again. Send him a note here. Andy, are you there? Now we can. You're back. Yes.
I'm not sure what happened. I apologize. I'm actually in Europe, and for some reason the internet cut out at the location that I'm at. So I really apologize. So if you can hear me now, just to go back to that slide. So it's really important to remember when we talk about particle size reduction, we really only talk about breaking up these binding forces and not actually destroying the particles. So that's usually some confusion, that comes up, but it's really about just particle size reduction and not destruction. Agglomerates and aggregates, these are these larger clusters, they're reduced to primary particle size. And I have a slide on that we'll go through in a minute here. And then really the shear forces are responsible for that separation, nothing else. So the higher the shear, the better our performance, and that will give us better particle size reduction. And then finally, we need good additives to keep our particles in a suspended state. And big additives is really good, and they can help with that. Okay, so here is a good slide just showing you different types of pigment classes. You can see yellow and TiO2. A lot of you probably are very familiar with that. And it just gives you an idea of how big these pigments are. Just a slide I threw in there. more visual. And so here you can see that that those larger clusters, these are called the agglomerates. And what we really want to do is in the pre-dispersion process, we want to break those up and we want to turn them into aggregates. Aggregates are the smaller clusters, smaller building blocks that circle in the middle. And if we want to go from the aggregate level down to primary particle size, that's when we really need to do the milling. So from agglomerates to aggregates, we use the Cowles plate. That's the pre-dispersion process. And then from aggregates down to primary particles, that's where we use the different types of milling technologies that are available, which we have a part 2 of this seminar where we dive into that. And at the end, John will send out an email and letting you know when that will take place. So in the dispersion process, it's really about wetting of these solid particles and the mechanical breakdown of these larger agglomerates and aggregates down to the primary particle size. And then at the end, as I mentioned, with the right additive, we have to keep these particles in a suspended state, and then we need to stabilize them. So Big USA are the experts in recommending the right additive for that. Okay, here is a great slide just showing you in the beginning with the Cowles blade, we are wetting our pigments or particles, and then we break up these binding forces, these Van der Waals forces, and usually not the case with every pigment. There are a lot of different pigment types, families, but what you're really looking for is about 10 to 20 microns of particle size, and at that point, it's better to start milling. We can introduce more energy, more efficiency. So in order for us to reduce the particles below 10 microns, usually we need to do some sort of media milling. Okay, here you can see kind of like the breakout. So we use a dissolver, again, as you can see on the slide, about 10 microns, so very efficient. And then we need to do the milling if we want to go smaller. With the right type of milling setup, we're able to go way down sub 100, sub 50 nanometers. Is not unusual with the right attachments. We have, nano kits and dedicated nano milling systems that can be utilized to really get down that particle size range. We also have some of the capability up in Wallingford at our our applications lab at Big USA headquarters. So if you have any products that you want to test or come in and take a look, we'll be more than glad to discuss that with you and have you up there. So we offer basically in this process, the dispersion process, a variety of different technologies, but in the pre-dispersion process, what you really want to look at, and that's the same for all the different types of equipment, is the tape speed should be between 18 to 25 meters per second. That's the sweet spot. That's where you want to be in. And basically, that's where you really start breaking up these binding forces. Anything less than that may give you the same results, but it will take much longer. Or in some instances, you may never get there and get these results that you're looking for. And we would use dissolvers for that actually with those blades. And then we have different types of systems, the SC for production, and we have a budgetary model, the LC. We have a really nice small unit for the lab space called the CV with different safety functions. We'll go through those. CN and AE are more of our higher end models with different upscaling capabilities and also data storage capabilities. And then when we talk about the milling, the fine dispersing, obviously we have different types of vertical bead mills, basket mills, and then also horizontal bead mills are also available for lab as well as pilot and production. So here is a very important slide, and it always comes up, is the diameter of the blade in proportion to my container diameter. And you're looking about 1/3 to, in some cases, 2/3. You can see On the right side, there is a nice table, and you can see that there is not one blade that fits every one container, or there's just one container, one blade per container. It was really a range, and depending on the viscosity, the flow pattern, you can really go and see, for example, if I have a 1 liter, it's about a quart, I can go all the way from a 30 all the way up to 70. So that's quite a bit range, but the sweet spot, probably what we do in the lab, is we probably use a 50 to 60 millimeter blade, depending on the viscosity, to achieve really good results. We have seen in some instances, if the viscosity is very high, we have to go with a little bit of a larger blade to move the product. And in some cases, for certain formulation, they require a smaller blade. But there is a really nice wide range of different blades. There's also many different blade types, so we have a good variety. I know that some of the other companies out there offer some very unique blade solutions. So go and check that out online. Then here, it's a very important calculation. It's actually, how do you figure out the tape speed? So the tape speed is actually the RPMs, multiply that by pi times the diameter of your milling disc. In this case, we figure out meters per second. So let's say you have a 50 millimeter blade, you multiply it by times 0.05, and then divide everything by 60, and that would give you meters per second if you want to calculate that. On our higher end disper mats, that's actually displayed on the control panel. You can see it. On the lower end models or the intro models, you have to calculate it. And so why that formula could be helpful. So we have a thing called the donut effect, and it's really called that. And the reason is, when you look inside of the container and you optimize the dispersion process, 18 to 25 meters per second, we have a really good viscosity range, and you should see something like that. And then you already know that it's very likely that you're optimizing the process and that things are getting properly dispersed. So that is called the donut effect, and that's really desirable in the pre-dispersion process. When you're milling, you don't really have a donut, but this is really something that only happens in the pre-dispersion process. So blade diameter, geometry of my blade in relation to my container size obviously plays a big role as well. If my blade diameter is too small, I will not be able to maybe get a donut. And if it's too large, maybe I won't have a donut either. So this is really about optimizing all the different variables, and then you should have a donut. Also, if the viscosity is really low, it's difficult for a donut to form because it would automatically collapse as soon as it has a chance to form. And when the viscosity is too high, let's say material is, again, like peanut butter, you will not have a donut because the product just wouldn't move in order for a donut to actually appear. So this is something you would see 3 to 10,000 centipoise range. When you optimize these variables we discussed, and you should really have a nice looking donut. This is what happens on the graph. So you can see where these, at the edges of the blade, this is actually where the separation of our particles takes place. That's where we break up these van der Waals forces. I would say that this also happens below the disc. It's not on this picture here, but you would have the similar effect also below the disc, not just on top. So that's something that I think is missing from that particular picture. Okay, here you can see definitely a good looking donut. We are running 21 meters per second, and at that viscosity range, we are able to put in 850 watts of energy to get that tape speed. So that's what you want. It looks great. Now, in this case, we're not so lucky, and our viscosity is different. We're only putting in 320 watts of energy at the same tape speed. That means our viscosity is probably a little bit too low, and we're not able to properly disperse this material. So what could help there is changing formulation to bump up the viscosity somewhat. You could increase the tip speed more than maybe a better donut could it be. Also, what could help is maybe change the blade diameter. That would also be something else that you could look at. That would probably help with putting in a little bit more energy. But that's something right here on this picture that's not desirable. We would call that a poor dissolver prep. And then we have obviously no donut effect on something like this, where we are running at 21 meters per second. So tips are okay, but we're putting in way too much energy. So here is the opposite effect. So the product isn't moving really all that well. The viscosity is really high, and we are having trouble actually seeing a donut. Could also be that we are still dispersing, but in this case, because of the high viscosity, it's just not possible that an actual donut forms. This is just a slide on dispersion result related to mechanical power. So P mechanical power 2 times pi times the RPMs times torque. That will give us the amount of energy that we're actually putting into our mill base. And on the higher end models, we actually show that we can also run our equipment with what is called constant power instead of just constant speed. That way you select a certain amount of energy you want to put in, let's say 1000 watts. And then the machine, depending on the viscosity of your material, will automatically adjust the speed to always maintain that amount of energy. So if our viscosity is increasing, our speed will decrease because we are maintaining the 1000 watts of energy. If our viscosity decreases, then our speed would increase because we're still maintaining that 1000 watt energy input. And that is something called constant power. And that is sometimes used also to calculate upscale costs or manufacturing costs, because it will tell us exactly how much energy we are using in a certain amount of time to manufacture or disperse X amount of product. So that can be very helpful. And that is a feature that we have on the higher end models like the AE or the CA. That option is available. We can also do what's called a net power calibration, just to mention that. That means that we run the machine without any product for, I think, 30 seconds. And then all the values get set to zero, the energy that it's using to operate itself, because the machine obviously is using power just to run the shaft, even if there is no product. So when we do a net power calibration, we factor out that influence or that noise, and then the numbers we see on the display are only related to our product and not the machine input. And that also is available on the higher end models. So in order for us to optimize our dispersion result, obviously duration plays a time. Here we are looking between 10 to 30 minutes, sometimes a little bit longer, or actually less time we have seen, but that's a good number for the pre-dispersion. We want to again see a donut effect. That would be ideal. And then the tip speed, very important. Try to stay within 18 to 25 meters per second. Not enough tip speed is just not going to give us the results in a timely fashion, or we may never get there. And if we're just putting in too much tape speed, it's kind of like the diminishing return. We're not going to really gain anything by going too fast. Geometric consideration again, blade diameter in relation to our container vessel diameter, 1/3, at least, is the ideal size. And then you can vary that depending on your viscosity. And then the right type of impeller disc. So again, there's different variations. So you can look on our website to see some differences. Some of our competitors offer other solutions, so they're very interesting. But this is something that you can go online and look at that. Then the amount of mill base. So we recommend at least 50%. That's a good number. If you have more than that, then sometimes you have an issue with product spilling over the container wall. If it's too low, okay, then you can't really maybe navigate the blade, oscillate the blade in the right position, and then sometimes you could end up hitting the container bottom with your blade. That's not ideal. Even though on our machines we have a safety feature called the working area threshold that actually allows you to lock in these positions, a top and the bottom position, so that you would never hit the container bottom with the dispersing blade, even if you lower it to the lowest position. Pigment and filler concentration, obviously very important. That's a formulation issue. We want to keep the temperature ideally as low as possible because we're putting in a lot of energy. And by low as possible, I mean it's the best temperature for your product. Obviously, if it's too low, in some instances, that will also increase the viscosity, which is not desirable. So you may have to disperse longer, or there's some other issues. So, but try to stay within room temperature. If you go too hot, obviously that's also a concern, especially if you're running solvent-based products. We want to stay away from that. We offer cool jacketed vessels, double-walled, for these applications, especially when you're milling. It's a lot more critical because that's when we're really introducing a lot of energy into our process, and we really need proper cooling. Not so much in the pre-dispersion process, but again, depends on the formulation, depends on the viscosity. Could also mean that you need to cool already during the pre-dispersion process. And then finally, obviously, we want to use the right additives that help us to wet our pigments more. Helps with the dispersing process, and then that the pigments, we don't want them to flocculate. And when we achieve all that and we have this desired particle size, and when it goes smaller, that's when we would go over and introduce our material into a bead mill. So the difference here is really with the dissolver, it's a necessary step. The pre-dispersion before I'm actually going to start milling. I have a limited amount of energy input. It's just such that a blade alone without media is just a blade. And will never allow for such a high energy input as you have a milling disc with media. So therefore our shear force is limited, and it's really only to deagglomerate. So we are going from the larger clusters, these agglomerates down to the aggregate level, and that's when we would use the dispermat or dissolver. And we're not breaking down to the primary particles with just a disc. But again, it's really critical that we use that step. And if we stop at the aggregate level, then obviously we're going to have appearance issues, and our product is just not going to be as consistent and maybe as desirable for the naked eyes if we would go and process this then in the secondary step with the media mill, where we're able to actually add a lot more energy, and then we really break down these binding forces down to the primary particle size, and that allows us to actually go sub micron range all the way down to sub 50 nanometers. We have seen that will give us a much better looking product, have better color strength, particle size distribution, transparency, haze, gloss. All these things should be affected by having a good processing step through a bead mill. So here's just an example of a standard. Well, this is actually our flagship model, but a really good basic laboratory scale benchtop disperser. In the smaller the units, usually the higher the RPM, because you need a smaller blade on a smaller unit. And in order for you to get to 18 to 25 meters per second on a very small blade, you need the high RPM capability. On our models, you can see the cowl's blade right here on the bottom of our shaft. But right below the motor is a flange, and that's called the quick disconnect, or the TML, a DL shaft, we call it. And it's basically a clamping ring that you can open, and you can rotate that whole assembly 180 degrees, and then you can replace the dissolver shaft, for example, with the rotor stator, or you can add a basket mill or a vertical bead mill, all on the same machine. And that is something that is patented with VMA to be so versatile with the quick change system. And it basically allows you to purchase one machine for many different types of applications. Um, so on this particular model here, we also offer what's called the C technology. That is a higher end software package, also a high end control module where you can actually see on the display all the critical parameters that you would need in the dispersion process that could be helpful to upscale. Obviously your speed is on display, the energy input, you have a value for torque represented in Newton meters, temperature readout, and the timer function. And actually the tip speed will also be displayed on that particular model. So that's the higher end Dispermat called the AE. You can see right next to the column on the bottom, on the right side, you see a little wheel. That wheel is used to actually tighten the container wall, the container clamp, and ensure that the container is perfectly centered and really tight, because you do not want a wiggling container during the dispersion process. It's if you can imagine, you run that at 20,000 and then the blade would hit the container wall. That is not a good idea. Um, the second safety feature we have is called the working area. I had mentioned that before. We have an upper and a lower threshold that we can set depending on the size of our container. And we do that electronically on the control panel. So basically, when the container is empty, you lock it in place with the wheel, and then you would lower the position of the blade to its lowest point before it hits the bottom of the container. And then you would lock that in. That is called H2. You just push a button on the control panel, and then you move it up to the top position right before the blade lifts up beyond the container wall. And we will call that H1. That's the upper threshold, because you wouldn't want to have a spinning blade at these RPMs outside of the container. And we have seen, if that safety feature is not engaged or working, and on some models that don't have it, then obviously somebody would have product splashed throughout their laboratory or actually could get hurt by the spinning disc. So that's why that safety feature is really important. And it's called the working area threshold safety feature. And then you can see on the Dispermats, it's also very important to our processing, is that we have a shaft guard that allows us to actually run the disperser without having any rotating or moving parts outside of the container. So that shaft guard, there's a little thumb screw right there that you can loosen and tighten to move that shaft guard up and down along the shaft to ensure that the shaft is properly covered when you are dispersing your material. Okay, then with these different types of tools, we have them, as a homogenizer. There's just a butterfly attachment or a propeller blade that allows you to turn that whole thing into a mixer or a homogenizer. You can also add a rotor stator, as I mentioned. That's an attachment that allows you to emulsify different products at a very high shear rate, and then you would basically mix them or emulsify these products. That usually is a good idea if the viscosity is very low, then that's a good tool to have. If the viscosity is very high, nothing would happen. The rotor stator would just basically stick in your mill base like a consistency of peanut butter, and there is no way that product would actually get pushed through these little gaps of the rotor and stator, so it wouldn't actually accomplish anything. So the viscosity needs to be really low for that to be effective. And then, of course, these are all out-of-the-box dispersers that have the capability of, obviously using it as the dissolver with the cowl's blade. That most of the models ship with a number of different blade diameters, Well, then you could convert them either to a basket mill by just attaching that with the quick change system, or add a milling disc and then use it as a vertical bead mill with our APS system. It's called an air pressure system. It's kind of vertical bead mill setup. That's really nice. And so here is a great picture where you can see just the standard disperser in the middle, and then all these different attachments that will go right on it to make that a cross-functional piece of equipment. So we got that rotor stator on the top left, and we have that APS I just mentioned. That's that vertical bead mill attachment on the bottom left, and we also could attach a wall scraping system. That is really important for very viscous materials, that you want to make sure that the product gets properly moved in and out and around throughout the container. It's basically a platform it's a rotating platform, and the sweeper blade is actually fixed, and then your container would spin once it's on the platform. And then basically, because it's on this spinning platform and the sweeper blade is fixed, that's what would move the product off the container wall and push it into the middle of our container, where then the dispersing blade will take over and do the proper dispersing of our mill base. On top right, we have a CDS system. That's our vacuum attachment. So for example, if certain products, are air sensitive, or like an adhesive, you don't want any air, then the CDS is very helpful in removing that, and then you can disperse under these conditions. It's a closed chamber with a viewing glass on top, so you can actually see what's happening during the process. So it's not like the container is completely enclosed and you don't see what's going on. You can actually see the process, and then you able to oscillate the blade, change the blade position, and then you can see that also what you're doing because of that viewing glass. On top right, we have that attachment. It's called a TML, and that is our basket mill. That's very helpful if you're trying to mill materials. So just briefly want to go through a few models if you're interested. This is our entry-level model. It's called the LC. Just very simple speed display. It's got a timer function, and that's it. You have to lift. I'm not a fan of it personally, because I like to have the electric lift capability that allows me to really lock in the right blade height in my container, and I don't want to do this by lifting up the motor head every time I want to change position. But that's what you have to do on the LC. You see that little lever right next to the motor on the stand, and that's what you have to open or close, and then it allows you to move the motor or the shaft up and down the column. It's okay. It's not my favorite, but it's comparatively an inexpensive lab scale solution. We also offer explosion-proof models in that design, but I want to mention they all run on 400 volt or 480 or 208, depending on the power in your building. So they're not single-phase. They're all the explosion-proof models are three-phase machines. Then we have the CV line, which is actually our most popular lab scale model that has the same capabilities as the LC, except you have now the automatic motor lift up and down, so you can really precisely position the blade in the container without having to do it by moving the motor up and down by hand. It has a timer function, obviously the display of our current speed, but this one will also give you a torque reading and product temperature. Product temperature is really important if you want to convert the CV model to a basket mill, or want to attach a basket mill or an APS, a vertical bead mill. That's when you really want to know what the temperature is during the milling process. So this particular model will give you that capability. Then we offer the CN, which is kind of like more a higher end model than the CV. You also have all the same safety features, but you're able to really upskill with this particular model to stay within the same model family. I can go up to about 50 gallons of material if I'm getting a CN 100, for example, and that would be allow you to really disperse large volumes for pilot scale, and the same machine would be available for small lab scale as well. So you would stay within the same model family if you're trying to actually upscale. Same control capabilities, speed, torque, temperature, and timer function. And then again, it has the electric lift motor to properly position the blade in the container. And also I want to mention all of our motors direct drive. We do not have any belts, so there's no real maintenance. They are brushless step motors. They're extremely quiet. If you have never seen one, at the next show, American or Western Coating Show, will have a model. Come up to the booth, we'll turn it on. You'll be surprised how quiet they are. You won't even know that they're running. And also, they have very low vibration. You could put a quarter on top of the motor, it would not even move because at high RPMs, because they're so quiet and so stable. And then we have the larger CN right here, same type of capability, except this one is now for small production or pilot. And then this is our premium model, which is called the Dispermat AE. That model, as I have mentioned before, comes with that C technology package. If you're looking for something where you want to have a recipe that you want to program, you want to store data on a stick or on a PC for later for creating lab reports. If you want to watch the dispersion process in real time on a graphical interface, then you have these capabilities with that particular model. It's really good for upscale. And you can get larger models, again, similar to the CN, all the way up, in this case, to 31 gallons of mill base. And also explosion-proof models are available. Here, same model except larger. And then we have the Dispermat SC for production, up to 2,000 liters of product volume. We also have the quick change system, which is really cool. For production, you have one machine that can act as a disperser, a dissolver, or a mixer, and then at the same time you can convert it into a basket mill with that quick change system. We offer vacuum capability for manufacturing. Some people also for lab space, but that's a manufacturing scale. Some people prefer, to do the dispersing process on the vacuum, remove all the air, and also doing milling. If you were to mill on the vacuum, it improves our milling efficiency. Imagine like these air bubbles in the mill base. They act like tiny little air mattresses, and they would actually buffer the blows of our beads if we were milling. So removing those air mattresses will get us better milling efficiency and a more homogeneous product. In some cases, we have the ability to add a nitrogen purging valve. Some people like to do that in a dry environment, so they want nitrogen or another inert gas, so that's also possible in our models to add that. Okay, quality control. So this on the left here is that C technology package. Again, you can see the RPMs on the top left. We have in the middle left, the energy input. On the bottom, the torque value in Newton meters. Top right is our actual tip speed, 20.4, temperature readout, and then we have a timer function. You can see that window on top right, those two little windows where you see a container with an impeller blade inside. On the bottom is that clamp of our Dispermat. So if they appear green, then you are safe to operate. If they appear red, then the machine will not run. So both the safety features, the container clamp has to be tight, and also our working area has to be established, and the blade where the milling disc has to be inside of the container. Otherwise, the machine will not turn on. On the right side, this is a different and very simple a control panel for our C model, which is good for production. It's very simple. Can't really break it. It's perfect for that type of environment. We have also that technology, LPC, where you actually make your own, create your own program or tie it into your own QC package. Some people have integrated scales. So with that solution, you basically control the process the way you want to control it, but you can also add different parameters that wouldn't be available otherwise. Now, the problem with this particular solution is that it's made by Siemens, and the lead times are excruciatingly long. I think the last I heard was like 12 months or 16 months lead time if somebody would want that particular control capability. On the higher model, we have the ability to program these called cutoff values. So we can have a recipe where we then obviously put in all the parameters that we want, even the height of our blade, timer, temperature, and then we have cutoff values. So let's say I have a temperature sensitive product. I can actually select, it has 2 warning zones and an action zone. So let's say I have 80C as my limit. I can have a warning at 60C, a warning at 70C, and then once it reaches 80C, we can tell it to either shut the machine off or run at a different speed. So there are some ways that those warnings signs can be dealt with. And you can have also cutoff values for the energy input or the speed if you're running with constant power. If you're running with constant speed, you can have cutoff values for your power input. So there's a number of ways on how you can modify your process. You can also see the entire dispersion process in real time and with these trend lines for each of these variables. And that actually allows you to monitor the entire dispersion process in real time. The net power calibration, I had mentioned that earlier. It's basically running the machine without any product for a couple seconds, and then it will basically factor out the load it's using to operate itself without product. And when you're running it with product, then you know all the values are the energy input, torque value are strictly related to your material. That's the software. Unfortunately, this is the old package. The Windows 10, the new one is not out yet. It still works. It's just dated in terms of how it looks, the GUI, but it's very functional and it allows you to basically monitor and log all the process parameters and the dispersion process in real time away from the Dispermat in your lab or office, wherever you have it hooked up. That's our applications lab in Germany. We have a lot of our different equipment, our attachments. We also have an upscale lab downstairs. So if you want to go and visit, please be our guest. We'd love to have you. But we also have capabilities at Wallingford, Connecticut, and we do the same thing. We love to have customers come in, and we want to do a proof of concept, show them how it works, and we also added some additional new capabilities. So we have the AE6 on the left here with that C technology for ultimate process control. We also have a brand new medium mill SL with a nano attachment kit that allows us to really mill down our materials to submicron into the very, very low nanometer range. Also with the C technology package, that what makes it really attractive is the whole line, same functionality on both systems, horizontal mill, vertical dissolver. Okay, so that covers it for today. For most, just a quick overview on the Wallingford lab. It's a high-end class facility. Again, we want to have customers in to do the demos, proof of concept. Also invite our colleagues from the big additives team into maybe the meeting or the lab and give advice on how to improve a formulation, or if there is an issue for flocculation or, a better binder, or, anything that will help improve the process or the product appearance, then we can offer those support mechanisms that we have in place. It's also great to leverage the synergy between the different divisions, and it's a showroom to show you. If you don't want to run product, just come in and see what we offer. And then finally, we can also use it as a milling or a seminar location. If you have a larger group, you want to come in, learn about dispersing, milling, we can have that also set up for that. And that's it for today. I think we're pretty good on time. I'll turn it back over to John for any questions.
Thank you, Andy. Great stuff as always. We appreciate your time and expertise. Have one question in here from Brittany, and she writes, for the bead mill method, in the dissolver step, would we expect to disperse until the donut effect was seen here as well?
So, hi, Brittany. Thank you for asking that question. So the donut effect actually is the result of dialing in the proper dispersion, pre-dispersion parameters. So when I see the donut, I would basically keep it there for about 15, 20 minutes, then take a sample, a quick, on the grind gauge, a quick check will tell us if we are getting better pre-dispersion results, and then we would move over to the milling. So at that point, when I verify, okay, I'm within my 10 to 20 micron range, then I can start, adding my basket mill. And start the milling process. I hope this answered your question.
Yeah, Brittany, did that answer your question? I unlocked your microphone, so if you'd like to chime in here, you can just unmute yourself on your end. If you're able to. If not, that's okay too. You can type a chat. Oh, that explains it. Thank you. Appreciate it. If anyone else has any questions, we just have a couple minutes left. Just type it in the chat function. Andy, while we're waiting for that, I guess what's the most frequently asked question you get when someone's getting into dispersion or looking to upgrade from lab pilot or to production?
Yeah, I mean, there is always obviously a number of questions. So how well does, for example, a lab dissolver, how well our VMA product like Dispersion, how well do they scale? Usually for most applications, we can expect about, at most a 15%, variance. And we have to make some adjustments, but they're very scalable. Our production from our lab to our production equipment. If you control all the parameters correctly, like the tape speed, the amount of energy we're putting in, the right geometry, then the results should be pretty similar. Of course, larger volume, usually we need a little bit more time, but again, about 15% more time is usually what we see in terms of upscale variance.
Okay, thank you. We appreciate it. In the chat, I also did put a link to the second part of this presentation, our media milling deep dive. It's scheduled for August 30 at 2 p.m. Eastern, same time as today's. There's a link there. You can just click on that and register. You'll also be sent invites for this media milling webinar, as well as our other webinar series topics. So with that, thank you, Andy. It's a pleasure as always. Thank you for joining us, and we look forward to seeing you on future Bic Gardner web seminars. Thank you, and have a great rest of your day.
Thank you, everybody. I appreciate your time today, and apologize again for the little mishap there with the connection.